Hello everybody. In this session I would like to go through a simple yet interesting problem in classical structural analysis. So we want to compare the vertical deflection of these two structures that I'm showing here on the left. The one on the top is a horizontal cantilever with a point load at the tip, and the other one is a cantilever inclined at an angle theta. Both of them have the same horizontal projection, L, and both of them have the same elastic properties and the same cross section. Initially, when you look at the problem, you immediately realize the reactions are the same in terms of shear force and bending moment. One of the cantilevers is obviously longer than the other. And so you begin to think in terms of simple solutions, right? You might say, well, in the horizontal cantilever, we know from basic structural analysis that the vertical deflection is PL cubed over 3EI. And then you may say, well, if now this is inclined at a certain angle, the length is longer because now that length becomes L divided by cosine of theta. So maybe the answer is something along the lines of P times L over cosine theta cubed divided by 3EI. Then you begin to wonder, well, but if it's at an angle, some of the force goes into axial force, and members are a lot stiffer axially than in bending, so maybe the deflection becomes less at some point when the angle is really high. So what's the answer? Well, first, let's just go through the classical solution. If we start by taking a rectangular cross section, height B, width B, and we look at the classical result from structural analysis, PL cubed over 3EI plus PL kappa 8G to account for shear deformations, we can substitute in the formulas and get a expression in terms of a few interesting constants here. One of them being the slenderness, which is L divided by H, and we're going to call that lambda, and the Poisson ratio, the shear area constant, and so on. We can see here that as the slenderness grows beyond 1, because it's cubed, the bending deformations govern the equation, and by the time the slenderness reaches values like 5 or 10, you're comparing things that are like 1,000 to 10. So as it's usually done, shear deformations are typically neglected for slender cantilevers. So this is all well known. And then we proceed to analyze the inclined cantilever here. And we know that in this case we're going to have axial, shear, and bending deformations. So we're going to use the theorem of virtual work. We're basically going to add the three contributions, and to do that we draw or calculate the shear, axial, and moment diagrams due to the loading, and then we calculate the shear, axial, and bending moment due to a unit load at the location and in the direction of interest for the deformation. In this case, that's vertical. We also realize that the part of the load that goes into shear is P cosine theta, and the part of the load that goes in axial is P sine theta. Again, we have to solve these three integrals, and we're going to start with axial. Simply substituting in the terms, we find the solution for the axial contribution to the vertical deflection, and it's this expression here in the box. We follow with the shear deformations and continue with bending deformations. One can initially realize relatively quickly that the cosine in this expression in the denominator is not cubed. If you remember at the beginning we said, well, is the answer going to be something along these lines of, and the answer is no. So that's not it. So that is the incorrect intuition. The answer actually, the bending effect, it just contains cosine of theta in the denominator, not cosine cubed. We add the three deformations and we get this nice expression here, which we can compare with the expression for the horizontal cantilever, and we see that it has a lot of terms in common, but it has some additional terms, especially in the shear and axial deformations. You can see this is the shear, this is the axial, and then it has this 1 over cosine term right here. If we plot the ratio of delta 2 over delta 1, the first thing we notice is that it's always greater than 1, regardless of the angle. So there is no angle at which the deformations in the inclined cantilever are less than in the horizontal one. And just to kind of get a sense of this, we also plotted here with different values of lambda slenderness. If you recall, we said lambda was L divided by H. And here you can see on the bottom, lambda equals to 1. So a really thick beam, and then on the top, lambda equals to 30, a very, very slender beam. So slenderness has an effect, but for regular values of slenderness, which for cantilevers usually range between 5 and 15, 5 and 10, it really doesn't have much of an effect. You can also see that at an angle of about 35 degrees, the ratio of the two deformations is about 1.2. So the difference is not that much, even at an angle of about 35 degrees. If we continue plotting this for higher values of theta, we find that something interesting happened. The answer shoots up and has an asymptote at 90 degrees. And about 60 degrees, the nature of the answer changes significantly. So we have here a kind of a sort of a steady growth behavior, and then after 60 degrees, things grow dramatically. And this function resembles the secant function, right? Which, if you recall from geometry, is 1 over cosine. And again, it has an asymptote at 90 degrees. So, very interesting, very non-intuitive in some aspects. So I thought I would share this problem with you guys and the solution, so you can see the application of the virtual work theorem and to improve your intuition in some of these problems in structural analysis.